to determine the forces that are developed in the wall, the different walls for this given configuration of a building, due to torsion that will come into picture, due to the eccentricity that we'll calculate. Okay, so if you look at this picture, there are how many walls? 5 walls in total. There are 2 walls along x direction and 3 walls along y direction. And if you look at it straight away, the very obvious thing would be that the center of mass and center of rigidity will not coincide. So the very first step that you will need to do is determine the center of mass and center of rigidity. So center of mass, can anyone tell me the coordinates directly? Hello?
5.5 comma.
Okay, where is center of mass located? It is basically the geometric center of the entire figure. So if you look at, one second. Yeah. So if this is 5, it is going to be halfway here. And if this is the entire thing is 4.5 plus 6.5 is how much? 11. So half is 5.5. So somewhere here. So if I draw these 2 lines, my center of mass is going to be at the intersection of these 2. Correct?
Yes, sir.
Okay. Now, how do you determine the center of rigidity? I'll call this center of mass. Coordinates will be what? 5.5, comma 2.5. Correct?
Yes, sir.
Okay. Now, talk about center of rigidity. How do we calculate?
Stiffness of the column into distance.
Okay, so we'll do it in this direction. You remember the sign convention we followed? We'll do this. So first for wall A, K into 0 plus 1.4K into distance is how much? 4.5
2.5
plus K into 11. The entire thing divided by K plus 1.4K plus K. How much is this?
$5.08.
5 point.
1 second, sir. $5.088.
Everyone got the same value?
Yes, sir.
Okay. So along this direction, it is at a distance of 5.088 from this origin point. Okay. So if this is 5.5 and this is 4.5, so we can assume that your 5.088 line is somewhere here. Correct? So
Yes,
you
sir.
can draw a line here. Okay. So this is your 5.088 line. Now for the other direction, I'll take the bottom to be the datum. So it will be 2K into 0 plus 2.5K into distance
5 meters.
5 meters, correct. The entire thing divided by 2K plus 2.5K.
2.78.
2.77. 778.
2.78.
Recurring, sir.
Okay, we'll take 2.78. Is this number correct? So if halfway
Yes,
is exactly 2.5, your 2.78 will be somewhere here, correct?
Yes, sir.
So if I draw a line here, the center of rigidity is going to lie here. Okay, so the intersection of these 2 points will be classed there in 1 hour. Okay, this is going to be our center of rigidity, whose coordinates will be 5.088, comma 2.78. Clear? Okay, now
Yes,
you
sir.
can notice that there is eccentricity in both the directions, correct? So this is going to be your EY, this is going to be your EX. Everyone has understood till here how to
Yes, sir.
calculate the eccentricity?
Yes, sir.
Okay.
Yes, sir.
Now just visually check if the values that you have gotten is logically correct. So if you look at these two walls in the x direction, it is 2 here, 2.5 here. So the center of rigidity has to be closer to the 2.5 K wall. It is closer, correct. Now look at the walls along y direction. There are 3 walls. In that, 2 walls are concentrated to one half of the building. So this 4.5, 6.5. So the left half has more stiffness. So it has to be more towards the left as compared to the right. That is also true. So halfway is 5.5. It is less than half the way. Okay, so visually it looks correct. So whatever values you have calculated, probably correct. Okay, what is the next step after finding out eccentricity?
Force.
We can open the code book. Okay, so in the code book, what does the clause state? For torsion, you have to, once you found out static eccentricity, you will have to find out design eccentricity. Correct? So for design eccentricity, there are 2 formulas. What are the 2 formulas?
1.5 into static eccentricity plus 0.05 into BI.
Where
Perpendicular distance.
first we'll solve it in one direction. Okay, so which direction do you want to solve first? We'll do x first.
X direction.
Yes, sir.
Okay, 1 second. Okay, first x direction. So first to calculate how much is the ESI we got in x direction. So eccentricity will be equal to what? It will be the distance from the center of mass to center of rigidity along x direction. So distance from center of mass to center of rigidity will be this 5.5 minus 5.088.
88.
Okay, how much is that? 5.5 minus 5.088. How much is this?
0.412.
0.412.
412.
412.
Yes, sir.
Okay. Next, once you've found out ESI, the next step is to find out EDI. Correct? So to find out EDI, you have 2 formulas. So under point 2, we'll subcall it point A, point B. So the first formula is 1.5 ESI, okay, plus 0.05 DI. The second is ESI minus 0.05 BI. Okay, but here, what is the value of BI that we should use?
5 meter.
So the definition for BI is what? It is the dimension of the base width of the building perpendicular to the direction in which you're considering the force, correct?
Yes, sir.
Okay. So if my force is acting along x direction, what was my building dimension perpendicular to it?
5.
5 meter.
Okay, x direction, perpendicular it is 5 meters. So take BI at 5 meters and calculate. How much do you get?
0.368. First.
First case is 0.368.
368.
Okay. Second case?
0.162.
First case is 0.88.
First one is 0.8, sir.
First case is 0.8.
First one is?
0.88.
0.868.
Second one is correct?
Yes, sir.
0.888 is it?
868.
868. Okay, 1 second. Okay, 0.868. Second one is 0.164.
162.
16?
2.
Okay. $162. Is everyone? Are these 2 values correct for everyone?
Yes, sir.
Okay. Now, once you found out ESI and the EDI values for both the cases, what is the next step?
Lateral force in the wall.
Correct. To find out lateral force in the wall, I should have mentioned it in the question. So along x direction, the force that is to be considered is 400 kilonewton. Along y direction, it is more walls, right? Let's say 550 kilonewton. Okay. Now, how do we solve this? Third step, force in walls. Okay. What are the two walls that is there in along the x direction?
D and
D and
E.
E.
correct. So to find out FD, it is going to be what? KD divided by KD plus KE
E.
into the force that is coming along
Yes.
x direction. Correct?
Yes, sir.
Okay. Now do this. Tell me what the value is. Similarly, for FE, it is going to be KE divided by KD plus KE into the force along x direction. So KD is 2.5K, K is 2K. So 2.5K divided by 4.5K into 400.
222.22.
200 and
22.222. Recurring.
okay. This will be 400 minus that, or
177 points.
187 point
177, sir.
177.7.88 allow 78
777.
are these two values correct?
Yes, sir.
Everyone?
Yeah.
We've got the same answer. Did anyone else get anything else? Hello?
No, sir. Correct, sir.
Okay. Now what is the next step?
Along Y. Lateral force due to torsional moment.
Before that, we need to find out something. To find out force due
R
to
value.
R value.
we need to find out the R values. Okay. Well, how did I tell you? What is our sign convention we follow for R values? So this
Upwards positive.
sign convention is positive, correct? So downwards and leftwards will be negative. We'll follow the same convention now. So I'll list all the walls: A, B, C. What happened? Something happened. One second. A, B, C, and then D, E. We'll write the R values. Okay. So for the first wall, wall A, what is the R value?
Mid of the shear wall.
What is R? It is the distance from
Center.
Origin to the mid.
origin, Allah, from that wall to
Center of rigidity.
center of rigidity. So from this point, center of rigidity is at a distance of 5.088. Correct.
So
So what is R?
5.088.
Ashter. What is the confusion there? Okay. For the second wall, wall B, how will I calculate?
Minus 4.5.
Correct. 5.088 minus 4.5. How much is that?
0.588.
0.
588.
588.
Okay. I have missed something in these two numbers. What is it?
Same.
Yeah, this should be negative. This should be negative because it is left of my point. Okay. Next, wall C, how much is it?
Positive.
It's the entire thing is 11, no? 11 minus 5.088. Why? How? Ishto. How much is 11 minus 5.088?
5.91
5 point?
912.
plus 5.91.
Okay, plus. Then wall D.
170.
Wall D is where it's on top. So it will be from the bottom, it was at a distance of 2.78, correct?
Yes, sir.
So it will be 5 minus 2.78. How much is it?
2.22.
2.22, and this will be 2.78. In this, which is positive, which is negative?
D is positive.
Are these values correct? Everyone? Everyone get the same values?
Yes, sir.
Yes, sir.
Okay. What is the next step after this? What do you do after SHEAR?
Lateral forces due to
Torsional moments are due to moment.
Let's call them FR, okay, or FT, whatever you want. So this is basically the forces that is developed due to torsional forces. For this, what was the formula? Ki.
KI divided by summation of KI square
Okay, into
F force, lateral force.
1 second. You know, after that. It stopped writing. Give me 1 second. It crashed. Okay, KIRI divided by summation KIRI square into
FED.
okay, and then I'll call this Fx because we're doing it for x direction, correct? Into something else.
Eccentricity.
Okay, which eccentricity?
PD.
ED.
EDI. Okay, now this formula that is there, you'll have to apply how many times?
The number of shear walls.
You'll have to apply how many times? One is obvious, it is the number of times shear walls are there. So 5 times for 5 walls. At the same time, how many other times you have to apply? You also have EDI.
2 times of
Along
eccentricity.
x direction, you have 2 EDI values. Okay, so what you can do is, you can probably make a table. Will it be easier if you do it in a table format?
Yes, sir.
Because your KI, RI value and everything will be common. So it is not like that in the solved problem, but now, so wall, okay, KI, and then RI, KI, RI, and then you have your KI, RI square, and then we'll do it for EDI 1, okay, EDI 2, I'll call it EDI 1x, EDI 2x. Similarly, when you do your y component, you will also get EDI 1y, EDI 2y, correct?
Yes, sir.
Okay. So, and then you'll have to multiply your values again. So I'll call them FR1. Okay, I'll call it FR1x, FR2x, FR1y, FR2y. The table looks big, but it is not too complicated. So first we'll start with walls A, B, C, D, E. Okay, Ki. What is the K for first wall?
K only.
K.
K.
Okay, second wall.
1.4 K.
Okay, K.
K.
D was 2.5, is it?
2.5 K and 2 K.
Okay. R we just calculated. What were the values?
Minus 5.088.
Okay, one minute. Minus 5.088.
Minus 0.588.
Minus 0.588.
Plus 5.912.
Plus 5.912.
2.22 minus 2.78.
Okay. Now what you need to do, multiply this. So KIRI is basically this into this. divided by KRI square. Someone tell me the values. Otherwise, should we do it on Excel? Will it be faster?
Excel is better, sir.
But when I apply formula and drag the cell, you guys might not follow it. What you do is take the values but solve the entire problem again. Okay, what is this? Wall.
K.
Wall. K.
R.
R.
KR. KRI square.
KI RI and then KI RI square and then EDI 1x, correct? EDI 2x, EDI 1y, EDI 2y, and then FR x1, FRX2, FRY1, FRY2. And let's start with this. Can I see the screen? Should I increase
Yes,
the size a little more? Okay, first A, then B, C, D, E. So quickly tell me the values again. This was K, 1.4K,
4.
then K again, 2.5K,
2.
and
2K.
then 2. What I'll do is I'll remove this. Then 1 and togolana because K numerator denominator ಎರಡು ಕಡೆನೂ ಇರೋದ್ರಿಂದ it will get cancelled. Okay,
Yes, sir.
but when you are writing in the table format in your notebook during the exam, keep the K there, or on top mention K inside brackets, taking K common or something like that. RI values was what? Minus 5.088, minus 0.588.
0.58.
Next.
5.912.
Okay.
2.22. 2.78.
Correct.
Yes, sir.
Okay. This is equal to KI into RI. Drag. This is equal to what was it? KI into RI. Correct.
Yes, sir.
Drag this. I need the summation of only the KI RI square term. Correct.
Yes, sir.
Okay. EDI value is what? For the first case?
0.868.
0.868.
Where is it? Did we not calculate?
Yes, sir, we did.
Oh, 0.868 and 0.162.
162.
0.868, 0.162. Correct?
Yes,
We
sir.
can calculate this, drag it. We similarly will finish off the calculations for EDY also here only. Okay.
Yes, sir.
So for Y direction, I'll write here Y direction. What is your BI value? 11 meters. Okay. Take 11 to apply the two formulas for this thing. Before that, we need ESI value. How to calculate ESI value? Look at the figure here. So ESI is the distance from center of mass to center of rigidity along Y direction. So 2.78 minus 2.5. Is it?
Yes, sir.
0.28.
0.28
meter.
Yeah. Now calculate the EDI values. Use the same formula. Substitute for ESI as this value and BI as this value.
Point 97.
Okay. Third decimal? Yenilva?
Illa, sir.
Okay. Next.
Minus 0.27.
Minus panta.
Yes, sir.
Everyone same values?
Yes, sir.
Brera confirm at least. Sure. Can we
Yes, sir.
proceed with this? Okay. 0.97 and minus 0.27. So 0.97 minus 0.27. Okay. Next, what do we have to do? What is your FR value? This is equal to KIR
KRI
divided by
divided summation
KIRI square. Okay. Into
force in x direction
okay, force in x direction ಎಷ್ಟು ಬಂದಿತ್ತು ನಮಗೆ
400 kilometer
okay 400 into
ED.
ಇದಲ್ವಾ
ಹಾ ಸರ್.
Are these the values? Check everyone once. Calculate for 2 or 3 walls, see if the values match. So basically your force due to torsion is equal to what? It is equal to KIRI divided by summation of KIRI square into the force that is acting along x direction, that is 400 kilonewton, into the design eccentricity for that particular case. In this case, it happens to be 0.868. Clear?
Yes, sir.
Okay. Individually check for 1 or 2 other walls and see if the values are correct.
Yes, sir. Matches, sir.
Okay. For the next direction, what do we have to do? For the next design eccentricity, this must be equal to
ED
KIRI,
extension.
okay, divided by KIRI square, this is frozen again, into what is the design force? Same 400 only, because the direction is the same.
EDI
EDI will use the second design eccentricity that we calculated. Okay, enter. Now drag this. Correct?
Yes, sir.
Has everyone understood this step?
Yes, sir.
If you want the formula, I will show it to you guys here. So this is the formula that we're following. Okay, this document also I'll probably send it to you guys today. KIRI divided by summation of KIRI square of all the walls into the force acting along that direction into the design eccentricity for that particular case. So each direction will have 2 design eccentricities. For now, that is why we have 2 columns for each direction. So you'll notice that we have said EDI 1x, EDI 2x. So this is for first case, this is for second case, but both are for x direction only. Similarly, we'll have to do for y direction. Okay, what is the formula again? This is equal to KIRI
divided by summation
KIRI square into what was the force acting along y direction?
550
into the design eccentricity for the first case.
EDI.
This must be equal to KIRI divided by summation KIRI square into 550 again, because the force along y direction is 550 into the design eccentricity for second this
Sir,
one.
wrong. FRI no wrong.
Oh, what did I select? I selected some wrong cell. This 1 second. This correct?
EDI. Yes, sir.
Look, check now.
Yes, sir. Correct.
Are all these values correct? This is very important to us. We will
Yes,
make
sir.
it okay, bold, everything will do. Now we've only solved one part of the problem. What part of the problem? Now we've only calculated the force that is arising due to torsion. But before this, we've done some other calculation. What is the calculation? We found out before torsion, just due to the stiffness of the walls, how is the force getting divided between the 2 walls in that direction? Correct? So you still have your 222 and 177 along x direction. The same calculation we'll also have to do for y direction. We'll finish that off.
Yes, sir.
Okay. So what are the 3 walls along y direction? We have FA, FB, and FC. Okay. So this must be equal to KA divided by Ka plus Kb plus Kc into your force in y direction.
550.
Force in y direction was how much? 550. Correct?
Yes, sir.
Substitute and tell me the value.
161.76.
And then I'll write off the formula for the other three. Calculate all three and keep. Kc divided by summation of all the three again. Kb plus Kc into force in y direction into force in y direction. Okay. How much is the first one?
161.76.
Anyone else get the same value? Snehali?
Yes, sir. Correct, sir.
Okay. Next wall.
226.47.
Okay. Next wall.
161.76.
Yeah, correct. It has to be equal. ಇವಾಗ ಇದಿಷ್ಟು ಆಡ್ ಮಾಡಿದ್ರೆ 550 ಬರುತ್ತಾ ನೋಡಿ.
Yes, sir.
Is this clear?
Yes, sir.
Yes, sir.
Okay. Now what we need to do, we need to combine these forces that are developed, okay, along with the forces that we've got due to torsion. Alva. So what I'll do, so we'll say along x direction, okay. Line gap, one second. This thing is stuck now. So I'll write it here. So let's call it x direction, okay, y direction, for the same walls. What is this? For the same wall. So A, B, C, D, E. So when the force is acting along x direction, what are the forces in walls A, B, and C? Look at the figure. When the force is acting along x direction, what will be the forces in walls A, B, and C?
0.
Correct. It will be 0. So 0, 0, 0. What will be the walls in forces in walls E and D? We calculate
Calculated
222.22 and 177.
37.7.
Raised to the 222.22 and 1.78. Correct. Well, next, when the force is acting along y direction, the forces along walls D and D will be 0, and the forces along walls A, B, and C will be as whatever we just calculated.
161.76.
You guys remember the values? 161.76. Amala
226.47.
Okay. 226.47. The last one is same, 166.76. Correct?
Yes, sir.
Okay. Now what we'll do, we'll define 4 new cases. I'll call them FAR. Okay. I'll call it FAR X1. Similarly, you'll have FAR X2. Okay. And then you'll have FAR Y1. And then you'll have FAR Y2. Correct? Now for the first case. So for FAR X1, it will be equal to this 0 plus the force that you got in this case. Correct? Yes or no?
Yes, sir. Yes, sir.
Yes, yes.
Okay. Similarly, you can drag this cell. So these are the forces that is developed in all the walls A, B, C, D, E, when there is a torsion along x direction for a design eccentricity value of 0.868. Clear? Similarly, what you need to do it for FAR X2. So this will be equal to what? The force along walls in x direction due to your static non-torsional case plus the force that is due to torsion for a design eccentricity of 0.162. Correct?
Yes, sir.
Now drag this. You get some values. Next, come to your y direction. So this will be equal to, now be careful which force you select. You have to take the force in y direction. So it will be equal to the non-torsional force distribution along y direction plus the torsional force that is developed due to design eccentricity of 0.97 meters. Okay, the last one will be equal to force along y direction plus the force that is developed due to the last design eccentricity of minus 0.27. Select all this, drag. Now, how do we select the final force in each wall?
Maximum.
Maximum of force.
Yeah.
Maximum of both.
So let's call this what? I'll call it FF. Final force in the wall, I'll call it FFW. Okay. Now, out of these four cases, what is the highest value?
170.2.
170.24.
I can do this, but in the exam, you guys can't do this. You guys visually inspect which is the greatest value and take that value. So for the first wall, it is 170.24. For the second wall, it is 227.844. Third wall, it is 197.158. Fourth wall, it is 243.846. Last wall, it is 173.736. Idralli, ivaga check madi if there is any wall whose value is less than, it would have been without the torsional component. So how do I compare that? So I'll call this F. I'll call it without torsion. Okay, without torsion. So without torsion, what will it be? So this will be the max case of the values that is there due to just simply dividing the force along that direction. Correct? So if you have to compare these values, so this is greater, no problem. This is also greater, no problem. This is also greater, no problem. This is also greater, no problem. Look at the last one. When I'm not considering torsion, the force that I'm getting is 177.78. Right? After considering torsion, due to all four eccentricity cases, somehow the value that I end up with is less than whatever I would have gotten without my torsion. Correct? So if we had to solve this problem using the old code book, you have to, which was that? What was that before 2016? 2002?
2002.
Yeah. So our code book nalli, you would have to replace this 173.736 value with 177.78 and design it for that. But in the new code book, there is no clause that mentions neglect the effect of negative torsion. So you guys do it for these values only. Understood this problem?
Yes, sir.
Yes.
Everyone?
Yes, sir.
Fairly simple. But the only problem is nimge illi it became too fast and convenient because we used Excel. In the final exam, I'm telling you this problem, if I give a problem with 5 walls, you'll easily spend half an hour to do it. Okay. So the same problem, what you do is I'll send the question on the group now. You guys try to solve it manually using pen and paper. And see how much time you guys take. You want me to explain again?
No, sir.
Yes, no. I'll quickly run through for everyone's benefit. So first, given a question, first find out your eccentricity values. How to find out eccentricity? Eccentricity is basically the distance from your center of mass to center of rigidity. How to find out center of mass? Always assume, unless otherwise mentioned, always assume that center of mass will always be the geometric center of the building. So whatever the planned dimension is, the base width 5 meters and 11 meters, whatever is given, simply divide it by 2. So 5 by 2, 2.5, 11 by 2, 5.5. So your x and y coordinates for your center of mass will be 5.5 and 2.5 in this case. Next, to find out center of rigidity, you will have to consider the stiffness of each wall. So along x direction, the parallel to along x direction, how do I say this? Perpendicular to your x direction, you have 3 walls, A, B, and C. So consider the stiffness. So stiffness of wall A is K into the distance from its origin. I'm taking the lowermost, bottom leftmost point to be the origin. So this is my 0, 0. Any calculation I make will be with respect to this point. So from this point to the center of this wall, the distance is 0. So that is why it is K into 0. Next wall, the stiffness is 1.4 K. Okay, so 1.4 K into the distance from here to here is 4.5. So that is your second point. For the last wall, the stiffness is K. K into the distance from this point to this point is 11 meters, hence 11. This entire thing divided by total stiffness, K plus 1.4 K plus the last wall K. Doing that, I get 5.088 meters. So we understand that the center of rigidity is located at a distance of 5.088 along x direction. So on this line. Similarly, do it for y direction. So along y direction, you have only two walls. Taking this point to be the datum line again, your 2K, okay, into the distance from this point to the center of this wall, 0 again, plus 2.5K into the distance from here to here is 5 meters. Divided by total stiffness in that direction, 2K plus 2.5K, you get the distance to be 2.78 meters. Drawing another line, you can locate where the center of rigidity is. Now looking at center of mass and center of rigidity, simply subtract one from the other, get the values for static eccentricity along x direction and y direction. We get the values to be 0.588 and 0.22 something. Okay, so we'll come here. So once you've got the design eccentricity, static eccentricity values, you will have to find out design eccentricity values. So to find out design eccentricity, there are two formulas that is given in the code book. So these are the formulas that is there in the code book. You don't even have to remember. Either you need two inputs. What are the inputs? You need static eccentricity and you need the base width of the building. This base width of the building is always in the direction perpendicular to the direction of force considered. So if I'm taking x direction, consider the base width along y direction. If I'm considering earthquake force along y direction, consider the base width along x direction. Doing that and using static eccentricity values, I've got two sets of design eccentricity values. Calculate them, keep them aside. Next, to find out force in the walls, first you need to find out force due to non-torsional condition, meaning when there is no torsion, simply due to the stiffness of each wall, how does the force acting along that direction get distributed? For that, the formula is fairly simple. So force in that wall is equal to stiffness of that wall divided by stiffness of all the walls summation into the force acting along that direction. When you do that, along x direction, the 400 kilonewton is split into 222.22 and 177.78. Similarly, along y direction, you have 550 kilonewton, which is divided into 161.76 in walls A and C. And for wall B, it has come up to 226.47. Understood? So these values that you have, this and this, is due to non-torsion. Okay, we have still not considered torsion. It is simply due to the virtue of stiffness of the walls only. Next, what we do, we have to find out the forces due to stiffness. To find that, we define a new term called R. R is basically the radial distance from the center of rigidity to each of those walls. So for all the 5 walls, you have to consider the value of R. So from this point, okay, I will take some other color. From this point, R to this wall is basically distance from here to this point. Okay, R to this wall is this distance. R to this wall is this distance. Okay, next to find out R for D and D, it is this distance. And for this wall, it is this distance. Doing this, you've got 5 values for R and we've listed them here. Okay, 5 values for 5 R's. I mean 5 walls. Next, what you do, you need to find out force due to the effect of torsion only. Now what you need to do, you need to see the number of design eccentricities we have. How many design eccentricities do we have? 4, 0.868, 0.162, 0.97 and minus 0.27. So we'll have to solve the entire problem basically 4 times using this formula. Okay, so this formula you will have to remember, it is not in the code book. So it is Ki Ri for a particular wall divided by summation of Ki Ri square of all the walls into the force in that particular direction into design eccentricity. So for 2 cases, force along x direction and force along y direction will be same, but each time your design eccentricity value will change. To solve that, we've used this Excel sheet. So we have what? We have 5 walls, the stiffness of all the 5 walls, R values of all the 5 walls, Ki Ri and Ki Ri square. So for Ki Ri square, find out the summation, keep it aside, and list the 4 design eccentricity values. So I'll explain how to calculate force for any one case. It will be similar for all the 4 cases. Ki Ri, divided by KI RI square into the force along that direction. So if there is X here, force along X direction was how much? 400. That 400 into my design eccentricity for the first case, 0.868. Enter. So similarly, do it for all the 4 cases with 4 design eccentricities, considering the corresponding value of earthquake force acting along that direction. So for X, we've considered 200. For Y, we've considered, for X, we've considered 400. For Y, we've considered 550. Doing that, this top table that is highlighted in yellow, we get forces that are acting due to torsion only. Okay. So for 4 cases of design eccentricities, we found out the forces that is developed in all the 5 walls due to torsion only. But we had already calculated the force that is there due to non-torsion. Now what you need to do, find out the algebraic sum due to this torsional case and non-torsional case. So non-torsional case thing you need to remember is, only if there are walls in that direction, you need to divide the force along that direction. Meaning, along X direction, if you have 2 walls, your 400 kilonewton that is acting will act only along those 2 walls. In the rest of the walls, you can consider it to be 0. Similarly, for Y direction, if there are 3 walls, the force will act along only those 3 walls, and the other 2 walls it will be 0. So for the first 2 cases, consider the force along X direction and add whatever values we've got here. For the next 2 cases, consider force along Y direction due to non-torsion and add whatever force we've got due to torsion here. Doing all this, we've got 4 sets of values. The final design force that you'll be using to design a shear wall will be the absolute max, meaning absolute andre, ignore the sign. Okay, see in this case, instead of this being 170.24, suppose it was minus 170.24. When I use the formula of max, it will show 131.296 as the highest value. You should not do that. You should use absolute maximum, meaning I'm ignoring the sign. I only need the magnitude. In this case, fortunately for us, all the values that are greater are positive in nature. So max is also worked. So use the absolute maximum of all the 4 cases. List them. That will be your design forces that you'll have to consider for shear wall design. That is all. Understood?
Yes, sir.